Hey everybody, today's lesson is all about the normal distribution. So this is really useful for looking at a lot of different kinds of natural phenomena, and we see this key phrase, normally distributed. When we looked at binomial distributions, that helped us understand how to make predictions based off of chance events, but when we look at the normal distribution, this will help us look at a lot of naturally occurring phenomenon. Okay, so let's go ahead and take a look at an example. Now, when we start collecting data and we start to graph it, a lot of times we put them into a histogram. And sometimes when we have enough data, we start to see an overall pattern that emerges and we can model it using a very smooth curve. Okay? Now this particular kind of smooth curve is what's known as the normal curve. This has very special properties to it that are repeatable in tons of different natural phenomena. If we were to start looking at the heights of all adult females or the heights of all adult males, if we start looking at blood pressure, if we start looking at IQs and we started measuring people's IQs, we will tend to find things that fit this kind of shape and they follow very consistent proportions. Okay, so there are some very interesting and helpful properties we can use to analyze data, and that is following a normal distribution, and we know that first of all as the empirical rule. So let's discuss that. The empirical rule is also known as the 68, 95, 99.7% rule. Okay? And it's going to follow this normal curve. Now, this normal curve is very special because it follows this empirical rule, and where we always want to start is we want to start at the mean, and that is mu. So we have the Greek letter mu. Remember, that's our mean. We learned this in year number 1. And then what we do is we start to break this apart into different equally sized or different sized chunks based off of the standard deviation, which we will call sigma. Right? That's sigma, and that is our standard deviation. And you may remember that standard deviation is the average distance an individual away is from the mean. I always like to call it my barometer of weirdness. Okay, and we'll start to see why something might be considered weird based off of standard deviations with the normal curve. So each one of these marks, we might call it a point of inflection, or we can start to look at this one is going to be exactly one standard deviation above the mean, and this mark is going to be exactly one standard deviation below the mean. And what's very special about the normal distribution and this empirical rule is that 68% of all of our individuals will fall within one standard deviation of the mean. Hence the 68 part of the 68, 95, 99.7% rule. And what we can do is we can then start to divide this out, saying, well, if that's 68%, and this is symmetrical about the mean, then that means 34% will lie on either side of the mean, within one standard deviation. Now, what about the next one? You'll notice that this space here is the same as this space here, which means this is going to be 2 standard deviations above the mean, and this is going to be 2 standard deviations below the mean. Well, you can probably guess what percentage that's going to be. That's going to make up 95% of all observations will be within 2 standard deviations of the mean. And then our final mark is going to be, again, another equivalent space, and that's 3 standard deviations above and below the mean. And what we can see here is that this is going to represent 99.7%, so the vast majority, almost 100% of all of our observations will lie within 3 standard deviations of the mean. So again, what is said that this is like a barometer of weirdness. We start to see things getting more and more unusual based off of where they lie as far as their standard deviations go. Let's try to break down this curve a little bit more. Okay? Okay, so we have accounted for 68% of all individuals within one standard deviation of the mean. But let's go ahead and now look at 2 standard deviations of the mean. Now we have 95%. If we take away that 68% that we've already broken apart in those first 2 chunks, that's going to leave us with 27% divided into these 2 equally sized chunks. Well, what is 27% then divided by 2? That's going to give us 13.5%. So 13.5% of all individuals will be from 1 to 2 standard deviations away from the mean. 13.5% will be above the mean, 13.5% will be below the mean when we look at 1 to 2 standard deviations. We can go through the same exercise by looking at the next groupings, where we see between 2 and 3 standard deviations, we have divided into these two equally sized chunks. Well, we've already accounted for 95% of them, but this is supposed to be 99.7%. So let's take away the 95 from the 99.7%, and we're left with 4.7% divided equally into these two chunks. And when we divide those into two chunks, we end up with 2.35% approximately will be between 2 standard deviations and 3 standard deviations above the mean, and between 2 and 3 standard deviations below the mean. And then we're finally left with just a super tiny chunk above and below 3 standard deviations of the mean. So these are extreme outliers, very unlikely to see any individuals that are more than 3 standard deviations above or below the mean, because we only have 0.3% to divide equally into those two chunks. 0.3% divided by 2 is going to be 0.15%. So now you may be wondering, like, how did we figure this out? Where did all of this come from? Well, it involved a lot of observation, a lot of calculus. This curve can actually be modeled with like a y equals x kind of function. It's just a really weird, gross, crazy calculus involved using the natural number e kind of function. And we don't really have the time to get into that. But if you want to take a look at this function a little bit more, if this is something that's extremely interesting to you, and you want to follow this up with maybe an internal assessment investigation, you can start to see how this curve is modeled by using your Cognitive textbook. Okay, but let's just focus on a couple of the main properties about the normal distribution that you have to know outside of this breakdown, the 68, 95, 99.7% rule. First of all, you need to remember that this curve is bell-shaped. That's usually how it's going to be described, as symmetrical, unimodal, and bell-shaped. It is symmetrical about the mean, meaning we have the same kind of breakdown to the left and to the right, which also means that we can say the mean is like the dividing point. That means we have 50% to the left and 50% to the right. 50% of the area to the curve is to the right of the mean, 50% of the curve is to the left of the mean, which tells us that 50% of all individuals will be more than the mean and 50% will be to the left of the mean. You might be thinking, well, that sounds a little strange. That reminds me of something else. That reminds me of the median, because it's the middle. And in this case, for a symmetrical curve like this, the mean and the median take the same value. They're equivalent. Moreover, we know that the x-axis is actually an asymptote to the curve, which means the curve never touches the x-axis. It's always above it, which kind of opens up the idea that an individual can potentially take any value. It may just be extremely unlikely. The curve is going to get closer and closer and closer, and the area underneath that curve, which represents the probability of that event happening, is going to be extremely small. Okay? So now, the other thing that we want to look at is that because this curve is supposed to represent 100% of all of our individuals, all possible values, we come to understand the area under this curve representing the likelihood of an event happening. And if we consider the entire curve, the area under that curve is going to be equal to 1. The area under the curve equals 1, or 100%, depending on how you want to look at it. So given that information, let's go ahead and summarize a couple of the findings that we have that are related to the area under the curve. Since the area under the curve is 1 and we know the mean divides it in half, what percent of the data is to the left of the mean? 50%. Same as what's to the right of the mean. As you learned, the data is broken up by using standard deviations, or sigma. And we said that 68% of all individuals will be within 1 standard deviation of the mean, 95% will be within 2, and 99.7% will be within 3 standard deviations of the mean. Let's go ahead and now take a look at an example to illustrate how we can answer probability questions related to this. The waiting times for an elevator are normally distributed with a mean of 1.5 minutes and a standard deviation of 20 seconds. A couple of things that you always want to be on the lookout for now. Look for that phrase normal distribution. It's going to pop up more and more frequently. Okay? With a normal distribution, that means you can draw that bell curve and you should be given a mean and a standard deviation, or you'll be able to find them with this information because this is how we define it. This is how we describe a normal distribution. We describe it using this notation, capital N for normal, and then include the mean and standard deviation. So this is just some shorthand to be able to describe it. So in this case, we have a normal distribution of 1.5 minutes and a standard deviation of 20 seconds. I want to keep the same units as much as I can, so I'm going to convert everything to seconds. 1.5 minutes is the same as 90 seconds, and then my standard deviation is 20 seconds. Okay? So now let's go ahead and sketch a normal distribution to diagram this information that represents the probability of wait times of this particular elevator. So we've got our normal-ish curve, right? In the middle is our mean, and that's at 90 seconds. And then we just want to start adding standard deviations to having these key marks that are roughly equivalent on either side. This is a sketch. You don't have to make anything too terribly perfect here, but now we're going to start subtracting 20 seconds to go on the either side. I like to usually write out my standard deviation somewhere off to the side. And the mean is very obvious that that's going to be 90 in the middle. So I usually don't need to make that mark. That's just understood. Okay? So we want to find the probability that a person has to wait longer than 2 minutes. Longer than 2 minutes, that's an important phrase because that's going to tell us which side we want to look at. And then 2 minutes and 10 seconds. Well, 2 minutes and 10 seconds, that's 120 plus 10 gives me 130 seconds. So we look for 130 seconds on our x-axis and we see that it's right here, and I like to draw that little cutoff. Longer than, we look at the right-hand side because that represents wait times that are longer than 130 seconds. And then we just need to see, well, what were each of these values? Here we had 2.35%, and here we had 0.15% because that was 2 standard deviations above the mean and 3 standard deviations above the mean. Adding those together, we have 2.35% plus 0.15%, and that gives me 2.5%. And that's it. Super simple. Seems like a really weird, arbitrary thing. How can I calculate the probability of an elevator's wait time with this information? I had barely anything. All I had was a mean and standard deviation. But we also knew that the distribution was normal. And once you know that it's normal, we can answer all kinds of interesting questions related to probability. So now, let's go ahead and look at this one more time, or look at the next example. Okay, find the probability that person waits less than 1 minute and 10 seconds. Well, 1 minute and 10 seconds, that's going to be equal to 70 seconds. So we draw that mark, and now we want less than 1 minute. So there's a couple of different ways that we can look at that. Less than 1 minute, 10 seconds, that's going to be everything to the left because that represents times that are less than. We want to know what is this area. Now, I could add together all three of these chunks between 50 and 70, 30 and 50, and then less than 30, or I can use this idea that I know that this chunk here between 70 and 90 is 34%, and then everything to the right of the mean is 50. And I'm looking for everything else other than that. So that utilizes the complement rule. So that's 1 minus 84, or 0.84, gives us 0.16, or we can look at it in terms of the percentage, and that is 16%. 100% minus 84% gives me 16%. And there we've answered that question. Super simple once we know the empirical rule. Now, let's go ahead and take a look at our next question. "200 people are observed and the length of time they wait for an elevator is noted. Calculate the number of people expected to wait less than 50 seconds. Well, expected, that's expected value, right? And expected value in probability distributions, that's as simple as E of x equals n times p, where n is our number of trials or our number of individuals times our probability of success. Well, n in this case is 200. We got 200 people. Now we just need to find what's the probability. We're looking for what proportion of people are going to be waiting less than 50 minutes. So that's this portion here. Less than is everything here. Again, this is the 2.35 and the 0.15. We know that's going to be 2.5% just by looking at the empirical rule. So now let's go and write that as a decimal rather than as a percentage, because that helps us with our multiplication. And we have 200 times 0.025, and that's going to give me 5. And now we can say that I would expect 5 people would have to wait less than 50 seconds for the elevator. Why is that going to be useful? Well, if I start to notice that there's a lot of more people that are having to wait less than 50 seconds, maybe the elevator's moving abnormally fast. Once I start to make that observation, maybe they're like, uh-oh, are the elevators starting to move out of control? Are we going to have just like this catastrophic elevator failure? This is how we use these probability questions. We start to compare observations to what we expect to see. And if there's a big difference, then something might need to change. Okay? All right, so that's the basics of using the empirical rule and starting to learn normal distribution. Thanks for watching. I'll see you guys next time.